The Pennsylvania State University, College of Earth and Mineral Sciences, Department of Energy and Mineral Engineering presents the Electrochemical Laboratory Instructional Video for Linear Sweep Voltammetry and Rotating Disc Electrode Measurements. In this video, we will demonstrate how to perform linear DC sweeps of electrochemical systems, as well as how to use a rotating disc electrode for hydrodynamic control of solutions. The test solution used here will use potassium ferrocyanide and its oxidation to ferrocyanide as the active electrochemical couple. Equipment and materials. A computer-controlled potentiostat for performing the DC sweeps. Test solutions. 1 molar potassium nitrate used as a background electrolyte and 6.4 millimolar potassium ferrocyanide as the active electrochemical species in 1 molar potassium nitrate solution. Both solutions are toxic and should be handled with care. 3 electrodes, a platinum working electrode, a platinum counter electrode, and a commercial silver-silver chloride reference electrode. A glass electrochemical cell with a rotating shaft for the working electrode, and a speed controller for the rotating shaft. Note that the working electrodes used here are not stable at speeds above 2500 RPM. Preparing the platinum working electrode. Before performing our tests, we need to polish the working electrode to provide a clean, flush surface free of contaminants or defects. First, the electrode is cleaned by rinsing it with distilled water and wiping dry. Polishing is done with a 0.05 micron alumina polishing solution. Make sure to shake the solution well before use. A small drop of this solution, about the size of a pea, is placed on the polishing microcloth. Gently rub the face of the working electrode against the microcloth, using the alumina particles as an abrasive to polish the platinum surface. Once the polishing has been completed, the electrode is rinsed again with distilled water and wiped dry. Assembling the electrochemical cell. This experiment will use a 125 milliliter glass electrochemical cell for holding the solution and electrodes. Always make sure to rinse any and all laboratory equipment before use. Connect the cell to the ring stand. The cell should rest on the white plate for additional support. The test solution is added to the cell using a funnel. For the first test, we will use the 1 molar potassium nitrate background solution. Once the solution is added, the working electrode is screwed firmly onto the rotating shaft. Lower the working electrode into the test solution. Make sure that the connection between the top of the working electrode and bottom of the rotating shaft remains above the solution level to prevent any leakage into the working electrode. Rinse the reference electrode with distilled water. Wipe dry and insert into the test solution. Repeat for the platinum counter electrode. We will now connect the electrodes to the potentiostat. First, connect the red counter electrode port on the potentiostat to the counter electrode using an alligator clip. Then, connect the yellow working electrode port on the potentiostat to the red port on the side of the rotating shaft. Finally, make sure the BNC connector from the reference electrode is properly connected to the reference electrode port on the potentiostat. We will now perform a background scan to examine the working electrode surface. Assemble the system as shown previously using the 1 molar potassium nitrate solution. Turn on the potentiostat. Hold the Control Source button until the light changes from panel to external. We will use the PineChem software installed on the computer to control the potentiostat. These are the test conditions to be used here. Once the conditions have been set, press Perform in the lower right corner to begin the sweep. The potassium nitrate solution should not have any electrochemically active species present. Thus, no significant levels of current should be passed between the working and counter electrodes until the decomposition potential of water is reached. If no major current peaks are observed, the electrode is ready for use. Some noise is expected from the sweep, as seen here. If larger currents are observed, there may be contaminants or defects on the electrode surface, requiring it to be polished again. Once a satisfactory background scan has been obtained, the system must be disassembled to prepare for the next test. Begin by disconnecting all of the electrode leads and removing the electrodes from the cell. When rinsing the equipment, always make sure to collect the rinse solution in a storage beaker for later disposal. If you do not suspect the test solution of being contaminated, it should be returned to its storage container for later use. Rinse the cell, again remembering to place the rinse solution into a waste storage beaker. The working electrode does not need to be removed from the rotating shaft, but it should be rinsed with distilled water and wiped dry. Next, we will use linear sweep voltammetry to investigate the kinetic behavior of the potassium ferrocyanide and ferrocyanide electrochemical couple. Reassemble the cell as shown previously, this time using 6.4 millimolar potassium ferrocyanide in 1 molar potassium nitrate as the test solution. We will again use the PineChem software to set up and perform the DC sweep. The first sweep will be done from a negative overpotential for the working electrode to a positive overpotential. This will allow us to observe the reduction of ferrocyanide to ferrocyanide when the working electrode begins serving as the cathode. The behavior of the current leading up to the peak can be used to determine the kinetic behavior of the system. The resulting data can be exported as a text file for later analysis. The test is repeated, only this time the sweep will run from a positive overpotential to a negative overpotential. This will allow us to observe the oxidation of the ferrocyanide produced in the first sweep back to ferrocyanide. If the upward and downward sweeps are identical, then the couple can be considered reversible. If the reaction exhibits a considerably smaller current peak or no current peak at all for one of the sweeps, then the couple can be considered irreversible. Upon completion of the test, the data could once again be exported for analysis. We will finish by using a rotating disc electrode to investigate the mass transfer behavior of the system. This test will utilize the same setup used for the previous linear sweeps. We will now use the speed controller to rotate the working electrode and control the hydrodynamic state of the system. The controller could be turned on using the switch found on the back of the device. Set the rotation speed to 400 RPM using the knob on the front. At no point should the electrode be allowed to spin above 2500 RPM, as this could result in damage to the electrode. Once the rotation speed has been set, we will use the PineChem software to perform a linear sweep. This time we are interested in just the oxidation of ferrocyanide and will only be performing an upward sweep. The sweep should show a somewhat flat current behavior at more negative potentials for the working electrode. This value is the limiting current, and it is the maximum current allowed by the mass transport limitations present in the system. This behavior could be observed in the first two sweeps, but at a lower magnitude when the solution was unstirred. Record the value of the limiting current once the sweep has completed. Set the speed controller to 900 RPM and repeat the test. Use the same sweep settings as was used at 400 RPM. The same current behavior should be observed here, only the magnitude of the limiting current is larger. This is because the rotation of the working electrode induces convection in the test solution. In an unstirred solution, mass transport is limited by diffusion of the active species to the electrode surface. Increasing the convection increases the rate of mass transport beyond that from diffusion and thus allows a larger limiting current. As before, record the limiting current value for later analysis. We will run a final sweep with a rotation rate of 1600 RPM. The DC sweep is performed identical to the two previous ones. The limiting current observed here should be larger than that observed at either 400 or 900 RPM. The Leibniz equation can be used to relate the observed current density as a function of the rotation rate. If the electrode area, solution viscosity, and concentration of the active species are known, then the equation can be used to calculate the diffusion coefficient of the active species. Conversely, if the diffusion constant is already known, then the concentration of the solution can be determined. Make sure to record the final limiting current value. Disassembly and lab cleanup. Once all testing has been completed, the system will need to be shut down and disassembled. Begin by setting the speed controller to 0 RPM and shutting it off using the rear switch. The electrodes can be disconnected and the cell disassembled, as was shown previously. Be sure to rinse and wipe dry all electrodes before storing. Also be sure to rinse the glassware before storage. Dispose of the rinsed solution from your waste beaker in the proper storage containers. Return any uncontaminated test solutions to their respective storage containers for later use. Once all other equipment has been put away, remember to shut down the computer and potentiostat before leaving the lab.